With
Thank you.
that, I'm now going to go into the next session. We have with us Mr. Binu Evamma Rolden, who's a technologist, computer vision and machine learning at Ittiam Systems Private Limited. He has over 2 decades of experience building software solutions for telecom, automotive, media streaming, and IoT market space. He has architected, designed, and implemented components spanning from device drivers to cloud systems to realize products involving multiple operating systems, including Linux, Android, GHS Integrity, VxWorks, and PSOS. Currently, as technologist, Binu anchors a computer vision, machine learning, and AI-based system for all retail analytics as well as video systems at Ittiam. Prior to Ittiam, Binu was working at Wipro Technologies, Bangalore. He holds a master's degree in computer science from Kochi University of Science and Technology, as well as a master's degree in physics from IIT Madras. Here to speak on low latency video capture, the challenges and solutions is Mr. Binu. Over to you, sir.
Hi everyone, I suppose I am audible enough.
Yes, sir. Very clearly.
Yeah, thanks for the introduction. I will just 1 minute share the presentation. Okay.
Sir, it seems that the video is zoomed in. If you have 4K turned on, could you please turn that off to 1080p in terms of resolution?
Oh, okay. 1 minute. Doesn't look like it is in. Shall I change the resolution to a smaller one?
Yes, please, sir.
Okay. Is this better?
So could you just stop and start sharing again? Yes, sir. This is now we can see the entire presentation. Over to you, sir.
Okay. Thanks. So, hi everyone. In this presentation, I will try to talk about the challenges with real-time audio on Linux and some of the recent solutions for handling this. Okay, so the presentation is structured somewhat like this. Basically, first we will look at how V4L2 is used for capturing video from a typical USB webcam module, and then the challenges with the evolution of this into a more complex camera pipeline, like what we would see in the current smartphone handsets. And then basically we will look at how frameworks like Pipewire is trying to solve the issues there. And then the last section basically looks at the Link Camera project and how its architecture helps us better. So we basically had a presentation on Pipewire by Olivier. So I guess he covered most of the audio related part. I hope, perhaps some of the part might be redundant and we might just skip that part. Okay, so to begin with, we will try to set the expectations on the camera access from a typical application developer's point of view. So a simple camera usage in that context can roughly be summarized in this 4 steps. The step 1 being getting the list of cameras in the system, identify which camera we have to use, then go and open the camera, configure any options like resolution or frame rate or whatever that is required. Then look at reading the camera frames and then do whatever is the real thing that the application is supposed to do. If it is just a simple camera, just show the video and or record the frames or whatever. And then close the camera and the application typically is done. So from this presidential use case perspective, perhaps the rest of the details of what exactly the application does or in terms of decoding and coding kind of a thing, perhaps we will keep aside, and only the low latency capture part is what we will basically look at. So in that context, ideally, the developer doesn't need or doesn't want to basically know perhaps a lot of details about the hardware that is involved and how they work internally. But they would surely want the application ideally to be portable across multiple platforms or multiple hardwares running Linux, obviously. And yeah, so that is kind of the expectation we will set for the rest of the slides or in this discussion in terms of the real-time video capture part. So, so we will look at this by taking a simple USB video device class camera, or whatever is typically known as the UVC camera. How the usage of the same basically is typically there in a typical desktop or desktop or laptop running Linux. Typically, even the most of the integrated webcams in laptops are also usually falls under the typical UVC camera class. And they basically have a integrated image processing pipeline, and so there may not be any need for a separate ISP or an image signal processor for handling many of these details. Okay, so from okay, so typically the stack or the entity which basically handles many of the cameras which are plugged into or all the cameras which plugged into the Linux kernel is actually through the video for Linux API, the video for Linux device driver. So it typically appears as a /dev/video device node in the file system. So the user space application typically just needs to open this particular entity, the /device/video entity, then configure whatever is required through some octal calls, then read and then close the device. So yeah, so the hardware specific details of how basically the different things are handled inside the device is something which the application typically doesn't need to bother about. Typically only you need to find out, you need to identify basically what is that X for opening the correct device. It actually in most cases can be a range from anything from 0 to 63. So since there is no direct enumeration support from the V4L2 perspective as such, there might be a bit of additional logic which will be externally required to figure that out. But otherwise, the application developer is typically it is basically his life is easy enough to some extent. Yeah, okay, there might be different codecs which might be involved in this particular case. Which is something which we again will keep aside for this discussion. So coming to the next case, this camera use case actually evolved a bit when Linux basically started being used much more in the embedded world. Practically, this no longer became the typical use case for many devices, particularly like smartphones or things like that, where there is an image processing pipeline which is part of the SoC itself. So in such kind of an embedded Linux use case, there are multiple reasons perhaps why this kind of an image processing pipeline which came into existence into the embedded world. One might actually be to lower the overall cost, or basically perhaps the size of the hardware, particularly in mobile phones, is typically a concern. So an integrated means an USB class device or a integrated device sitting there might actually be adding to the thing. But perhaps the more interesting or more real reason might actually be what this kind of a topology enables. So for example, with an image processing pipeline directly accessible to the main CPU, there are lots of options which are now open basically for enhancing the image in different ways and updating it on the fly without really a new hardware iteration and things like that. So yeah, so this things like even a face detection based autofocusing mechanism or things like that are things which this kind of a topology enables in a big way. It also in some sense is also related to yeah, as I said about the SoCs which are available for the this particular use cases for the embedded case. So also if we are talking about Intel SoCs, when they were also attempting entering the smartphone or embedded world in this kind of a devices, perhaps around that time we also have the IPU3 support, an image signal processing support, which came in KB Lake, or even there are more recent iterations in more recent hardware. So we will move on to look at how a typical image processing pipeline is there in this kind of a complex hardware. So what are the typical things which has to be additionally taken care of? They include typically that the raw image or the raw data from the sensor typically might have to go through a bare sensor data conversion to RGB and to YUV format. Then there is also the 3A algorithms, basically the auto exposure, auto white balance, and auto focus. There might also be other image enhancement mechanisms, including, say, lens correction for, say, basically Vindushin kind of a thing, or vignetting for corner sharpness or corner shading, basically. When noise control, basically denoising the scene, and other enhancement, even basically the black level of the sensors, basically for that, again, you might have to adjust the values, basically, so that the basic black level itself is identified. So one another interesting point to note here in that context is basically that for many of these algorithms, the ISP interface which the SOC provides is many times considered as proprietary information basically by the SOC vendor. So as a result, support for these are typically coming out as closed source binary blobs, which okay, from an open source Linux community perspective is something which is the expectation is typically different. There are concerns about lots of undocumented IOCTLs or things which are used even when there are things the interfaces are basically exposed to some extent. And typically, the stability again under Linux is something which many a times comes into question if the focus is not really there from the device vendor in that sense. So yeah, so keeping those aside, basically coming to the image on the right. So this actually is a diagram for the TA OMAP3, a slightly old SOC, which was used some time ago. Okay, this is used because this was one of the ones where details of them was easily available in the public domain as such. So if you see here, basically there are quite a few of the yellow boxes which are basically representing the device nodes which are exposed by the drivers. So there are multiple video capture /dev/video nodes and multiple sub-device nodes exposed in addition to the media controller itself. So controlling this hardware basically requires opening the media controller device, setting up the pipeline, then adjusting the sub-devices, and then using the video nodes for streaming. With basically a typical application that we were talking about in the beginning, using V4L2 API for doing all this is what is typically expected in that context. So actually, if you look at it, so these many number of device nodes are being handled by the application is something which doesn't make this application very portable per se. So the challenges, if we look at it, is that with so many of these complex pipeline which is brought about by the direct usage of V4L2, it becomes very difficult, and often it affects the portability of the application as well as the maintainability of the code base, and then the overall application development timeline also becomes perhaps a bit too much involved or a bit too big to handle in that sense. So one of the initial attempts to improve this basically was a library which was known as the libv4l. So it consists of a few components, including the libv4l convert, which was taking care of the format conversions and does some of the image quality enhancements part as well. So this basically handles there were libraries to have for the libv4l2 for the v4l2 part, and as well as the old v4l1 emulation part. So this was practically even for applications which were not already compiled with libv4l2 or libv4l compatibility. There was a compatibility layer which can be used to intercept the calls using a LD preload and then redirect them to the libv4l functionalities. But okay, this was perhaps not really an ideal solution, as it turned out to be something which was practically not really well maintained for many of the complex pipeline use cases which are there. Again, the conversions many a time were not really fast enough for a real-time use case with typically with embedded hardware kind of a thing. And so there was attempts to look elsewhere for the solution, and that is where we come across pipeware as one of the solutions. So as Olivier was talking about in his presentation, originally the idea was basically inspired by Pulse Audio. So in fact, it was even called as Pulse Video in that context initially. The idea was to improve it by the way the Pulse Audio was handling the audio part in the overall picture. So perhaps I may not go too much detail into this slide since we have already discussed this in the different context here. So one thing to note, basically, yeah, perhaps here is the extensibility through the simple plugin API or through SPA plugins which are there available. So I guess I will go to the next slide. I suppose Trust is something which we basically have, I think, was better covered in Olivier's presentation. So looking at the current status of Pipewire, basically, as it was explained, Pipewire audio server has replaced Pulse Audio itself. Okay, yeah, again, it is interesting to note basically that it was originally Pulse Audio that inspired Pipewire to come up in the first place, but then around 5 to 6 years down the line, basically Pipewire itself replaced Pulse Audio. And so Fedora, as it was said, is something where Pipewire is the default audio pipeline or the audio server. Also, AGL, the automotive grade Linux, was something which was also discussed in that context. And yeah, I suppose there are particularly the Bluetooth stack support part was something which was appreciated as well. So coming to basically the video part of the support, yeah, again, there was the Wayland Compositor is something which helps in the video screen sharing use case for the use case like what we are having in this Zoom call as such. But beyond that, basically the camera support, native support for cameras was something which actually was still limited to the simple V4L2 pipeline integration. So complex cameras per se were again expected as separate SPA plugins which had to be integrated in. But one of the interesting developments in that part was basically that a little over a year ago, there was a lip camera plugin, which means lip camera based SPA plugin, which got integrated into Pipewire for the video capture, which can enable us to even use the complex camera pipelines. So let us now take a look at what lip camera basically is about and what it brings to the table. So lip camera basically is a complete user space camera stack. It basically supports basically the supports multiple camera devices with support for enumeration. So you don't need to guess the devices directly, the div nodes directly, or things like that. You can basically try to figure out what all are the devices which are available in the system. And then it also supports multiple concurrent streams for the same camera. And it basically also supports controlling the capture parameters. Hello? Hello?
Yes,
So please
Mr.
go ahead.
Binu, you are audible.
Oh, okay. I heard some noise in between, so I thought I was not audible enough. Okay, thanks. So basically, okay, so lip camera supports basically also controlling the capture parameters for each stream basically on a per frame basis. So the lip camera stack as such, so basically there is a core lip camera framework, and on top of that basically there is a set of adaptation layers for the different use cases. So basically there is a V4L2 compatibility layer to emulate a higher level V4L2 device with perhaps the same level of features as a USB webcam only. But the more interesting part perhaps is on the right side, where there is support for the Android camera HAL. I think currently it is with 3.3 or whatever that is supported. This again, the adaptation layer also is something which comes from the lip camera project itself. So it basically is something which is designed looking at easy integration into basically Chrome OS as well as Android. In fact, the Chrome OS itself also uses the Android camera HAL itself for example, running even the Android based applications as well under Chrome OS. Then there is also a GStreamer based plugin which is currently being done by the lip camera team itself, which might later on perhaps be moved on to the GStreamer project altogether. But yeah, currently that is something which is also available as a adaptation layer component. So yeah, as we briefly discussed, so the intention here is basically to support most of the Linux distros out there, say Ubuntu, Fedora, or RHEL and all the others, theoretically in that sense, plus Android and Chrome OS, basically. So particularly, I guess the team works pretty much in, they have basically in close contact with the Chrome OS team as such, basically in terms of support and other things. So yeah, so okay, going into the architecture of the lip camera internally. So you can see basically on the there is basically a camera devices manager, which is basically the entry point thing for the applications to enumerate basically the cameras in the system and identify the list of cameras and select one of them and do all the sorts of the camera management in terms of configuring and other things. It also basically provides the hot plug notification mechanism for camera removal, or like the USB webcam removal insertion kind of a use case. And so then what is there is the camera device itself. So the camera device itself actually composes of a device agnostic part and basically a device specific part. So the device specific part consists basically of two components majorly. It is basically the image processing algorithms part as well as the pipeline handler part. So both of this basically needs to have the knowledge of or basically needs to know about the vendor specific details. So the pipeline handler per se is is actually expected to be an open source component. But the image processing algorithms themselves can be including, it can be a closed source component, but the point is basically that you can't make direct calls basically to the v4L2 layer or directly to the kernel IOCTLs, basically directly from the IPA part. The image processing algorithms part is forbidden. So in case if it is basically a closed source binary library kind of a thing, then it is expected to be running in a separate process, and it is supposed to be, the data is supposed to be available through memory maps and or memory sharing, and there is a marshalling API to communicate with the IPA component itself. And it basically runs in a separate sandbox environment. So coming to basically, coming to the details basically about this algorithm, perhaps basically typical things like the 3A and other algorithms that we briefly discussed earlier is what it typically composes of. And then we basically also have a set of utility libraries or helper and support classes in the form of the media controller and v4L2 for v4L2 interactions. Then for buffer allocation and basically then the sandboxing IPC for the IPA part. And then there is also a plugin manager and pipeline runner and a few other things. One thing which I think I forgot to mention in the previous slide was basically about, so the lib camera itself is implemented in C++, and there is a API which, there is a public API for lib camera which is supported from that sense, but there are also additional language binding options for different languages, like say for example, the natural one basically there will be a C API, but beyond that also other language bindings are something which is expected from for camera applications in other let us say languages per se. So going on to the next slide, so already, so this project basically was supported, I started, I suppose, sometime in the 2018-19 timeframe, and in the current status basically is that it actually supports many of the, or practically most of the core functionalities one way or the other. It supports multi-camera use cases, the multi-streaming, per frame control, and camera hot plug, and among other things. But the API basically is not yet frozen, the public API for the lib camera. It is, there is an, so it is expected perhaps in the shorter time frame. But as we mentioned earlier, there is already a pipeware support, for example, using the current, one of the recent pipeware versions, lib camera versions already in the pipeware repository. And from a platform support perspective, currently there are pipeline handler support for the USB webcam, obviously, and some amount of some variants of IPU3 itself is actually supported in the code base. Then Rockchip RK3399, NXP IMX7, and Allwinner A31 are things which basically are already supported in that sense for the pipeline handler part. And one of the interesting other things to note here is basically for the Raspberry Pi 3 and 4, they have basically moved to lib camera earlier this year with a open source reference implementation, so to say, which includes both the pipeline handler as well as the image processing algorithms part. So this basically the image processing algorithms part are assumed to be in a near in a very production quality kind of a implementation that is available. There are so all three cameras which are there, the Omnivision as well as both the Sony sensor, which is as well as the high quality camera module. All three basically are supported through this pipeline, and there is also a detailed tuning guide which is available from the Raspberry Pi Foundation in terms of configuring them as well for different functionalities. So yeah, so basically the combination of the pipe wire and the lip camera in the current form, I guess addresses most of the concerns which we which we discussed in the starting of this presentation. So we can use the lip camera directly for certain kind of functionality for image applications, or perhaps or perhaps pipe wire basically for more complex applications, or maybe multimedia applications, which involves both video and audio, might be recording for real-time synced audio and video, might be something which helps the application developer community in a big way. So yeah, that is all basically that is there from my side. So the references, yeah, is which we have used is something which is listed in this slide. And thank you. I suppose it is now open for questions.
Yes, absolutely, Mr. Binu. We've received a few questions from the members of the audience here, but in the interest of time, we'll be taking only one question.
Okay.
Yeah, Mr. Binu, a very interesting talk that we had today, and with everyone working from home, it's pretty interesting. Like, people are using the cameras and the video far more, and it's good to have not a difference or backlog of audio and video playing in different time. So there is a question that's there for you. We'll take up one question. So can Pipewire support both, like, different types of cameras? Can we actually have instead, say, a LiDAR or a thermal camera or some other similar input device, and have the application just deal with it on the same set of APIs?
Okay, interesting question. Okay, so from a camera feed handling in Pipewire perspective, yes, there can be there can be basically plugins which are written, which can be written basically for handling different kind of camera devices itself for integration into the Pipewire. And yeah, the Pipewire standard APIs will, I guess, suffice for using them. Yeah, I guess that answers that question.
Sure. Very well. Thank you so much, Mr. Binu. And it was great listening to you today. Over to you, Fatima.
Thank you so much, Mr. Ankit. And of course, a big thank you to Mr. Binu for conducting this entire session. Thank you so much for making it here to the Very Large Data Engineering Summit 2021. We've truly had an absolutely innovative and a very interesting session with you, Mr. Binu. Thank you so much once again.